Hello students, welcome to another lecture in our course Environmental Modeling and Simulation. In today's lecture, we are going to talk about limit cycles, how they are important. I must tell you, limit cycles are quite hard to identify. They're not as simple as identifying a saddle point or a stable fixed point, unstable fixed point. You remember the tau versus delta diagram that we discussed earlier, where you could map very easily based upon the tau value and delta value from your characteristic equation to identify the behavior of the flow lines, trajectories around the fixed point. Limit cycles are not that straightforward. They require, actually, this is where the computational power that we have now becomes really beneficial. The approach to identifying limit cycle is typically based on elimination. There are ways to identify them without eliminating, but we are going to browse over the whole field of limit cycles basically to understand them and how to use them when needed in environmental cycles. I talked about this in the previous lecture, that in environmental cycles such as the seasonal cycles or the seasonal cycles of nutrients in any environmental matrix that change with seasons or with any other oscillation, limit cycles are typically what we see. We do not see centers, we see limit cycles. So things in nature tend to have a rhythm, many things, not all. And if there is any fluctuation outside from the rhythm, there is any aberration, the tendency of the system is to return back to the orbit, to return back to the rhythm. And that is the behavior of limit cycles. But there are three different kinds of limit cycles, and not all of them return back to the limit cycles. Some of them run away from the limit cycles given an opportunity. That's an example of an unstable limit cycles. So to begin with, let's try to understand the three broad ways in which our limit cycles look like. So let's say we have an orbit. So let's say this is our orbit and things are flowing in this direction, and any aberration from this orbit. So let's say we are starting from inside the orbit. Let's say it flows like this and eventually joins the orbit, returns back to the orbit. And let's say we are starting from aberration that goes outside the orbit and we are again returning back to the orbit. Oops. Not intersecting. Remember, flow lines don't intersect. Flow lines don't intersect. That's going to be a cardinal mistake. Don't make it. So let's say we are returning back to the orbit, right? And it will be a smooth return to the orbit. Just so that you know, this is a classic case of a stable limit cycle. So I'm going to highlight your limit cycle. This was your limit cycle. This is a case of stable limit cycle because trajectories around this limit cycle, limit orbit, they come towards the orbit, they become one with the orbit. Some limit cycles, some orbits look different. So let's say this is another orbit and it's also flowing in the same direction. And if the trajectories around it are behaving like so, let's say the aberration brings the point here, the face point here, and now it's moving away from the orbit, not towards the orbit. Let's say the aberration brings the face point here and now it's trying to escape the orbit. Now this is an example of an unstable limit cycle. And then we have the third kind of limit cycle. So let's say this is our orbit. And if there's an aberration that brings the face point inside the orbit, let's say it's behaving like so, running away from the orbit. And if there's an aberration that goes outside the orbit, let's say here, and then it's moving towards the orbit. So it's moving towards the orbit in a very smooth way and becoming part of the orbit. Yeah. So this is an example of a half stable, so stable on the outside, half unstable on the inside limit cycle. From environmental perspective, from perspective of things that we see in a natural world, in life, stable limit cycles are essential. I want to quickly clarify, a limit cycle is not same as having a center and an orbit around center, because these are isolated orbits, very important. What it means is that there is no other orbit inside or outside these orbits. So if I had an orbit that looked something like this, and then inside it I had another orbit, like a series, an array of orbits, and outside also I had, which is what we see in case of centers. Then this is not a limit cycle. Limit cycle is different. It's an isolated instance. It has an isolated orbit. So as I was saying, in environmental systems and in life systems, stable limit cycles are very important, and each limit cycle, each orbit will have its own periodicity, its own amplitude, its own waveform. And if there's any aberration, in case of stable limit cycle, things will try to come back to the orbit, come back to the limit cycle. This is, as I told in the last lecture and also in the introduction of today's lecture, these are important in context of heartbeat and in context of other seasonal cycles that we see in the environment. Also, when we have self oscillations that can become very dangerous, for example, in case of airplane wings or in case of bridges, typically this is what we want, that after we have had oscillations that are aberrant, the oscillations return back to the stable limit cycle, stable orbit. Now let's take a very simple example where we have a stable limit cycle and try to see how we interpret things. Again, as I said in the introduction, limit cycles are pretty hard to ascertain. So we are going to use the concept of null lines to understand how the flow is happening, and then we'll talk about identifying limit cycles. So a very simple example to begin with. So we are looking, because we are looking at oscillations, we are looking at, in the phase portrait, what appears to be motion around a center or motion in an orbit. We are going to talk about radius and angular velocity. So the radius is r, angular velocity will be given by theta, how the angle is changing, how theta is changing. So the radial dynamics will be dr by dt. And d theta by dt will give me angular dynamics, how the angle is changing. Because now, since we are talking about limit cycles, we do not require our orbits to be perfect ellipses or circles. They can be anything. Something like this can also work. So r is changing with time, and so is theta. Both are changing. So what we need is an equation for dr by dt and equation for d theta by dt. And we are going to start with the simplest equation, and then we are going to see how the limit cycle looks like. So let's say d theta by dt is equal to 1. To make life very easy, angular dynamics is constant, and dr by dt looks like this. This is radial dynamics. So now, since this is a very simple system, we can actually look at dr by dt and see how r is changing with time. Treat this like a 1D system. It's not dependent on theta, right? And theta is not dependent on r. They are uncoupled systems, the easiest kind. The next example that I'll give will not be an uncoupled system, it will be a coupled system. So you will use the null line method, but here they are uncoupled, so we can treat them individually. So when we look at how radius is changing with time, r 1 minus r cube, it can be treated as a 1D system. So let us draw the phase portrait of this system. So if you remember 1D system phase portraits, what we do is we look at how the variable on x-axis is, and the velocity, the rate at which the variable is changing, which in this case is the rate at which the radius is changing, or radial dynamics on y-axis. And now we are going to draw the phase portrait. So for phase portrait, first thing you want to find out the fixed points. This system r 1 minus r cube has how many fixed points? We find out by equating it equal to 0. So definitely when r is equal to 0 is a fixed point, and then the other fixed point is when 1 minus r cube is equal to 0, which means r cube is equal to 1, which means 1 is another fixed point. So these are the two fixed points of this 1D radial dynamic system. And now to draw the phase portrait, we need to find out what is the sign. Now between 0 and 1, r is going to be positive, because r is between 0 and 1, it is positive. And 1 minus r cube, since r is less than 1, this is also going to be positive. So dr by dt is going to be positive. So here it is positive. Now beyond 1, when r is more than 1, r is going to be positive, but 1 minus r cube is going to be negative. So dr by dt is going to be negative. So what our phase portrait in this instance looks like is something like this. Again, remember these are qualitative phase portraits. Something like this, yeah. Now stability is going to be very easy to determine. When the phase portrait is above the x-axis, flow is towards right. I hope this is a revision of our initial classes. When the trajectory phase portrait goes below the x-axis, it is negative, the flow is towards minus infinity, negative. So clearly this business here is unstable and this is stable. So look at what's happening. This is giving me an idea. Since the radius has a stable fixed point at 1, r equal to 1, what it is telling me is that if I look at how r is going to change, very clearly and obviously, radius as 1, r is equal to 1 is a stable fixed point for r, which means if we are starting at r equal to 1, then the r does not change. So this is definitely an orbit. I do not know if it is an isolated orbit making it a center, non-isolated orbit making it a center situation, or it is an isolated orbit making it an limit cycle situation, but it will be clear very soon. Clearly we know there is an orbit and that it has a fixed r1, so basically it's a circular orbit because r is fixed. Okay, now what happens when r is less than 1? When r is less than 1, the r increases, see? di by dt is positive. When r is less than 1, so let's say I'm starting from somewhere here. I'm going to use a different color for this. So let's say I'm starting here and r is less than 1. As theta, d theta by dt is equal to 1. So as theta changes, as time changes, following this angular dynamics, r is going to eventually increase. R is going to increase till it approaches the orbit. So the flow line is going to look something like this. If r is greater than 1, so let's say I'm starting here, r is greater than 1 to begin with, yeah? This is r naught 1, this is r naught 2. When r is greater than 1, look, the flow of r changing with time is towards left side, r is going to reduce, we are going to come towards r equal to 1. So basically the flow line is going to look something like this. Something like this. It's going to come towards the limit cycle, towards r equal to 1 orbit. So 0, 0, 0 is unstable. So if I'm starting at 0, it's going to be like this. If I'm starting outside, so what I'm seeing here, and I hope it's pretty clear to you now, that we are dealing with the situation of a limit cycle because the flow lines around r equal to 1 move towards r equal to 1. They are not moving in circular fashion around the circular orbit. So here we are dealing with a situation that's a stable limit cycle. Now you may say that, hey, we just drew the phase portrait for r, treating it as a 1D system, we have not drawn it for r and t. You can actually make that, but for purpose of this course, understanding this much is sufficient. Now we are going to take another example. It's an example of glycolysis, and it's a very fascinating model. So let's get started on this. So glycolysis is a process with which living beings, living cells, many of them are single cell organisms, some of them like ourselves are multicellular, multi-organ organisms, use glycolysis to convert glucose into energy. So we are basically trying to get glucose into energy. And we have noticed this through our varied experiments and observations that glycolysis undergoes oscillation. And we want to understand, does it undergo limit cycle based oscillations with an isolated orbit or not? Now this is very important because if we have an isolated orbit and it's a stable isolated orbit, then we know that even if there are variations in glycolysis over day due to changes in environment or due to threat or whatever situation, disease, eventually the organism will try to bring the glycolysis back into the orbit. If it is a stable fixed point, then we know that glycolysis is going to be same, it's not going to oscillate regardless of what happens, which may not be very conducive to life. Sometimes we need glycolysis to get up. Okay, so the model for glycolysis, if we non-dimensionalize it, looks something like this. Okay, the X here represents adenosine diphosphate, which is an energy molecule inside our bodies, ADP, ATP, adenosine triphosphate, diphosphate, that ADP. I have an entire NPTEL course on environmental microbiology where I talk about ADP and ATP in detail. The Y here stands for F6P, which is fructose 6 phosphate. So, the X and Y, the levels of ADP and fructose 6 phosphate in the cell oscillate, and this is the model, and it was given by this scientist whose name I don't know how to pronounce. I'm just going to write it down. In 1968. So, we know that ADP and F6P undergo oscillations, and we want to figure out what kind of oscillations they undergo. Now, one thing that we can do is write the characteristic equation right away, but more informative than that, in case of trying to figure out limit cycles, whether it's an orbit that is isolated or not, null clines will help us. So, we are going to do the null cline system. So, we are going to find the x null cline and the y null cline. So, x null cline is when derivative of x with time becomes equal to 0. So, in that case, we have minus x plus a y plus x square y equal to 0. So, y is equal to x by a plus x square. This is your x null cline, and then our y null cline will be when derivative of y becomes equal to 0. So, what we get is b minus ay minus x square y is equal to 0, which means y is equal to b by a plus x square. So, you see they are quite easy, interesting equations we have gotten. Now, let us put the null clines on our phase portrait. So, y on y axis, x on x axis. Remember, x is ADP and y is F6P. So, the x null cline looks something like this. I am going to write here x null cline. And this is y null cline. Of course, it depends upon the value of a and b, but we know this is how the system looks like. Where these null clines intersect, here, this is where you have a fixed point. Now, we don't know if this fixed point is the center of the orbit, if it is telling us that, hey, there is an orbit around it, or if it is a stable fixed point or a center or a saddle. We have no idea. We are going to do the null cline system to understand it better. But we know there is a fixed point here. So, once you have drawn your null clines, the next step is to understand the flow around the null clines. So, we'll go through the different regions and try to identify the flow. So, let's look at this region first, the biggest region, this region that I've highlighted in yellow. So, in this region, what's happening is that the y is more than, so this is our x null cline. Now, we want to find out what is the sign of x and y derivatives in this highlighted region. That will help us understand the flow in this highlighted region. So, here we are above the x null cline, we are to the right of the y null cline. So, if you look at the x null cline here, we see that the y is bigger than it should be to be on the line. So, basically here we know the dx by dt is going to be positive. And then let us look at the sign of y derivative. So, for y derivative you need to look at y null cline. So, you have y null cline here, and the x here in the y null cline is bigger than it should be to be on the null cline, and this is your x component here. So, we know that if this was equal to 0, if the x was perfect to be on the line, this would be 0, but since x is bigger, dy by dt is going to be less than 0. So, here we see that x is going to increase, y is going to decrease. And then let us look at the other highlighted portion. So, for all the regions, we are going to find out the signs of x and y. So, this is the light gray region that I am painting here. We are going to look at this region. So, in this region, we are below the x null cline, we are still to the right of the y null, right and above of the y null cline. So, below the x null cline, right, so let us go to the x null cline, which means y is less than what it should be to be on the null cline. So, x derivative is going to be negative. Now we are still to the right of the vinyl line and on the top of it, which means y derivative is still going to be negative like it was in the yellow highlighted portion. Now let's highlight the other portion. So let's look at this portion. Which I've highlighted in light orange. Now here we are still above the x null line, which means that y is bigger than it should be to be on the null line, which means dx by dt is going to be positive. So we are going to have x dot positive. Now we are inside the vinyl line, which means x is lesser than what it should be to be on the vinyl line, which means that y derivative is going to be positive. Now let's look at the fourth place in our null line diagram. So if you look here, we are under the x null line, which means x derivative is going to be less than 0 because y is less than what it should be to be on the null line. And we are also under the y null line, which means that x is less than what it should be to be on the y null line, which means y derivative is going to be positive. Okay, now we are going to draw the flow lines in this area and try to understand the behavior of trajectories around the intersection of null lines, which is where the fixed point is. Let's look at the yellow highlighted portion. X derivative is positive, y derivative is negative, which means x is going to increase. So x is going to increase, y is going to decrease. So the net flow is going to be in this direction. Let's look at the gray region. So net flow is going to be in this direction and I've shown it with the red arrow. Now in the gray region, x derivative is negative, which means x is going to reduce. In x direction we are going to the left and y is negative. So in y direction we are going down. So net movement is going to be here. Now let's look at the blue region. In the blue region, x derivative is negative, which means x is going to reduce. So in x we are moving towards left side. Y is positive, so in the direction of y we are moving up. Y is increasing, so net flow is in this direction. Now we are looking at the orange portion, which is the orange highlighted region, which is the only region left. And in this, both x derivative and y derivative are positive, so we know the net flow is going to be in this direction. So you see, around the fixed point, we see some kind of circular movement. We see some kind of flow that is happening in a circle. Now this could mean that the fixed point is a center, definitely not a saddle. Fixed point could be an isolated limit cycle. We do not know that clearly, but we do know that if some things are in this region, so let's stick with the red color. So let's say we have a starting point here in the yellow region. We know that there will be a particular area here where beyond which this red point will not be able to go. So let's say that theoretical area, let's highlight it in black. So some area, we do not know what that area looks like, what its size is, but qualitatively we know there has to be an area, and I'm going to highlight over it with a this area which I've highlighted with gray now. We know that if there is an initial point or any phase point which is in this area, it will not be able to escape this area. So how the flow lines will look like for this point is like this. Let's say we are starting here, it is pushed here and then it moves, whether it moves in spiral in, moving finally towards the limit cycle, or spiraling in towards the fixed point, we don't know. But we know that this point this trajectory will not escape this gray area. So this is known as trapping region. Whenever we find a trapping region, we see that since the trajectory cannot escape this region, either it has a fixed point where it will go, like a stable spiraling in fixed point, which we know it has a fixed point, we don't know if it is a stable fixed point, or it has a stable center or stable limit cycle. We know something very interesting is happening. And this is where the theorem, which I'm going to give you now, comes into picture. It's a very important theorem. And I don't know how to pronounce the name of these European scientists because, I'm not familiar with the language, so I'm just going to write down the name. And I hope I got the spelling right. So we are going to introduce, I'm going to introduce you to this Poincaré-Bendixson theorem, and sorry for butchering the pronunciation completely. I'm sure I don't pronounce it correctly. And then we are going to continue our discussion of the glycolysis model. So what is this theorem, Poincaré-Bendixson theorem? Poincaré-Bendixson theorem says, so we have a dynamical system, dx by dt is equal to fx. Okay, and we have a closed system in the phase portrait. Let's call it R. R is for region, right? It's a closed system, and within it there is some trajectory that is following this system, and this system is continuously differentiable. So basically it has unique solutions. Unique solutions exist for this domain. And yeah, and R is a closed space, and this, there is a trajectory that's moving in. Let's say this R is a closed space that does not have any fixed point. By closed space, it means that the trajectory is not going to escape R. So R can, trajectory C will not escape R. So we have Poincaré-Bendixson theorem. It's saying we have a closed trapping region R, and we have a trajectory that is following a continuously differentiable dynamic system. So we know that it has unique solutions that exist. C is not going to escape R, and there is no fixed point inside R. No fixed point inside R. So if there is no fixed point inside R, then there is only two possibilities. Either C itself is an orbit, possibility 1. And then the possibility 2 is that C finds and joins an orbit. So if there is no fixed point, there is an orbit. And if there is a fixed point, then it could be a stable or unstable fixed point. Why is this important? Because if we go back to our system here, our glycolysis system here, I'm saying because two null lines are intersecting each other, it has to be a fixed point. But there's also a possibility that this is not a fixed point, but there is an orbit here. That possibility also exists. So let me highlight orbit in a different color. And the orbit might be big, small, we do not know what shape or size it will have. But if it does not have a fixed point, then it will have an orbit and all the trajectories will go to the orbit. But if it has a fixed point, then the fixed point will determine how the trajectories move. So in today's lecture, we talked about limit cycles. We talked about, I introduced you to a very simple limit cycle example, and then we started discussing the glycolysis model, and I told you about the trapping region. And when you see a trapping region in your null-line flow diagrams, you should start thinking about whether, because in trapping region now we are dealing with R, the trajectories are trapped, they are not going to leave. So is there a fixed point inside it? If there is a fixed point, then the fixed point will determine the movement of trajectories. If there is no fixed point, then Poincaré-Bendixson theorem comes into the picture, where either the trajectory that we are dealing with itself is on the orbit, or it is going to move into the orbit, it's going to join an orbit. And that's all for today's lecture. In the next lecture, we are going to continue a discussion on glycolysis model. We are going to solve it. We are going to try to identify whether it has a fixed point, or this place here is actually showing us a fixed orbit, an isolated orbit. Not fixed orbit, sorry, isolated fixed orbit. That's all for today in this lecture. So see you in the next lecture. Thank you.